Hello, multivariable calculus students. We are continuing our work with section 11.4, and we're going to talk about differentials, which is on page 23. So here is our review of differentials from single variable calculus, and this is a concept that we learn kind of right in the middle of the year. We talk about some of the applications of derivatives and the tangent line itself, and we always draw out this diagram. I always remember this because everyone's eyes kind of get big as I start to label all this stuff. Usually it's an AB calculus, the first year of calculus. People kind of get overwhelmed by all the different labels. And notice as you scroll your eyes down the page, we add a few extra labels. So it's a little overwhelming, but I promise you it's going to be simpler than what it looks. But just bear with me here. So here's our old diagram, and the idea here is that as you look at a tangent line in single variable calculus, and you look at it touches a curve at one spot, and that point right there is perfectly aligned between the curve and the line. So they are equal to each other. As you move along the tangent line, you hypothetically you pull away from the surface, and when you pull away from the surface, there's a difference then between the change in the y value on the surface, or on the curve, excuse me, and on the tangent line. The x values, however, are identical. So as you move horizontally, your dx is the change along the tangent line, and your delta x is the change along the curve, and they're equal. As you look at the change in y, however, the dy is the change along the tangent line, and the delta y is the change along the curve, and those are not the same, but they're an approximate of each other. And so we use the idea of this differential. So the differential is going to be the dx and the dy. We're going to throw in now a dz. The differential we're analyzing here is just the little bits of change that occur along a tangent line, or in our context, the change along a tangent plane. And it's a way for us to estimate the change of the actual. And often we'll use differentials when maybe the actual is really difficult to calculate, or we would need some sort of computer-generated system to calculate. So thinking back to single variable calculus, we talked about how our derivative f of x is equal to the notation dy over dx, and our differentials are going to be dy and dx. The differential dx, for example, is the change in x. dy is the change in y, so the little increment change of each. If you were to just simply solve for dy, you would have the derivative of f times dx, and that is an analysis of the differential dy and how to calculate it. So when you look at the differential dy and you want to know what is that actual change, you can take the derivative and multiply by the differential dy, the derivative of the function. Now keep in mind that this is completely aligned with the idea of a tangent line itself. So for example, and I'll make the same connection with our concept with a third variable. So think about it this way: if you have your change in y, the dy, that's simply just your y value minus wherever you started. That's going to be your change in y. In a similar way, you have your so these two are aligned. You have your change in x, and that's simply just the change in x. So really, a lot like the linearization concept we just talked about, it's really the same thing you've been studying. It's just a way to talk about it differently is what a differential kind of is. So differential is going to be the conversation behind what the actual change in the variable is, and the notation looks sometimes drastically different, yet it's completely connected to the tangent line. And what we're going to find with our differentials is that our kind of notation behind it is going to be a little bit different, but it's directly connected to everything that we've been doing so far with the tangent plane. So here's your formula for the differential dz, and notice that you have the partial derivative with respect to x multiplied by the differential dx, and the partial derivative with respect to y multiplied by the differential dy. You could write it differently if you want. Okay, so here's the connection. You have z minus z sub naught equal to the partial derivative with respect to x multiplied by x minus x sub naught plus the partial with respect to y times y minus y sub naught. So take a look at the similarities, as I just mentioned. So you have your differential dz and you have your change in z. You have your differential dx, you have your change in x. You have your differential dy, you have your change in y. It really is just a different way of writing the tangent plane equation, and that's what we're talking about now. Now you can look at the rest of the text that we have here with regard to the different representations. The idea is that the actual function value is approximately the function value at the point at which the tangent line touches the surface, plus whatever differential we have in terms of a change. So this differential is approximated by the tangent plane, and it just calculates the possible difference or movement away from the point of tangency. So we have our point here at which the tangent plane touches the surface. As we kind of scope out past that point and we look at what's happening to the behavior of the plane and the behavior of the surface, we can see that they're not exactly the same. And so the idea is that we often cannot calculate the change in the actual function because maybe we don't have enough information, maybe we don't have a computing system, or maybe we're just being challenged to do it without something like that, who knows. So instead of being able to do this with something more complex or maybe with more information, we can calculate dz by taking the tangent plane and approximating dz through that, which is often a much easier calculation, and then applying it to the information we know, which is the point of tangency. So that's the idea. You can see that there is so much more here. There's lots of different variables and all this kind of stuff. All it is saying is that we can predict the change in x and the change in y exactly. And you can notice that it's written that way right here and right here. So on the surface, on the tangent plane, the change in x, the change in y, because they're the independent variable, those changes are identical on the surface as well as the tangent plane. However, the two kind of unknowns here, or comparisons here, I should say, the dz we can find pretty quickly without a whole lot of pain and suffering. The delta z is the one that we often cannot find, and so we use these, which are not identical, to approximate themselves. Okay, so that's what we're going to do here with the differentials. All right, let's go to the next page and try the first example. Okay, example 6, we're going to talk about the differential versus the increment. The bottom line is the differential is the estimate, it's the dz. The increment is going to be the delta z. So I'll spoil that right away. So this is dz, this is delta z. That's the whole terminology thing. Okay, so if z is equal to that equation, we want to find the differential dz. So we're going to simply calculate the partial derivatives. So we have 2x plus 3y, and for y we have 3x minus 2y. Remember, dz is equal to the partial with respect to x times dx, and the partial with respect to y times dy. So we're just going to simply substitute this in, and we don't really have anything we're analyzing yet, so we're just going to leave this in variable form. So there we have it. If we had more information, whoops, sorry, hold on, which we will in a moment, then we could calculate the actual differential dz. So that's our formula. Okay, let's take a look at an actual problem now related to this formula. So we have x changing from 2 to 2.05 and y changing from 3 to 2.96. Compare the values of the actual delta z with the approximate dz, or the increment delta z with the differential dz. Okay, so we're going to take our formula that we have there. We do need to know the partial derivative evaluated at the point at which the tangent line touches, which is 2, 3. That one is going to be, it's going to be 4 plus 9, so that's going to be 13. And then we have the partial with respect to y, which is 2, 3. And that one's going to be, that's going to be just 0, 6 minus 6. And we do need the differential dx, which is just, again, the change from 2 to 2.05, so that's just going to be 0.05, and dy, which is going to be from 3 to 2.96, so that's going to be negative 0.04, And we just have to simply substitute this in to the formula above in blue. So we have 13 multiplied by dx, which is 0.05 plus 0 times negative 0.04. So we just need to take 5 times 13 and adjust our decimals there. So we have dz equal to 0.65. That's considered the differential. That's our approximate, okay? Now the actual is going to be the delta z. And so our delta z is something we would have to do with the calculator. And it's going to be f of 2.05, 2.96 minus f of 3. So you would take the above equation here, and we're going to substitute in 2.05, 2.05, and 2.96 and 2.96. We're going to calculate that, which is here, and then we're going to subtract the point at which the tangent line touches the surface. So we're going to put in, substitute in 2 for x and then 3 for y. And I'm going to do that on my calculator. Okay, so what I get then from that is 13.644, I'm going to round, so 449, and then 13 for the original at 23. So this, of course, gives us a increment, or the exact value of 0.6449. That's going to be pretty close to what we calculated there, which was 0.65. And again, we did our calculation without any kind of calculator. That's kind of one of the main reasons for using differentials and that kind of an approximation system. All right, let's try example 7. So example 7, we have the base and the height of a right circular cone, and it is measured as 10 centimeters and 25, respectively, with possible error in measurement of as much as 0.1. So we're going to assume here, based on the context of our text never gives a plus or minus error. So this is just a positive error. So in other words, the minimum radius is 10, the maximum radius is 10.1. The minimum height is 25, the maximum is 25.1. So we're going to use differentials to estimate the max error in the calculated volume of the cone. Don't know if you have it memorized, but the volume is 1/3 pi r squared h. So we have, and it might help. Let's see. So this is just an equation v of two variables r and h. So this is a 3-variable equation. We're going to essentially have to figure out what is the differential dv. What is the error in the possible calculated volume? So what we're going to do is take our knowledge of the differential and say, okay, we're going to take VR, so we're going to take the derivative with respect to R and multiply by the differential dr, and the derivative with respect to h and multiply by the differential dh. So we're just using different variables here. It's the same basic idea. So let's go ahead and calculate VR, which is 2/3 pi times r to the first times h. And we're going to do VH, which is 1/3 pi r squared. Okay, we're going to calculate this at our values. So let's go ahead and just kind of outline what we have here. So the R value is 10, the H value is 25, the DR is 0.1, and the DH is also 0.1. So we're just going to take our formula and just plug all of this in. So I'm going to take this formula. I have dV, and it gives me 2/3 pi times R, which is 10, times H, which is 25, times dr, which is 0.1, plus VH, okay, that's going to be 1/3 times pi times R is 10, oops, sorry, squared, multiplied by DH, which is 0.1. So I'm going to highlight all the different parts that we have. So the VR is here, and the VH is here, and then the DR is there, and the DH is here. Okay, so I'm going to erase those highlights, but that's where all the different parts line up. Okay, let's get rid of all that. I'm sorry. Okay, now our task is to simplify this down. So we can do a little bit with this. For example, the 10 times 0.1 is going to be 1. So we have 25 times 2 over 3. So we have 50 over 3 times pi. We can do a similar thing. We have 10 squared, but 10 times 0.1 is going to be 1. So this gives us 10 over 3 times pi. So that's 60 over 3, which is 20 times pi. So that's going to be our estimate. Now what I'm going to do, just so we can see if this is very close at all, is that we're going to find the actual. So this is the approximate, and I'm going to use a calculator to find the actual. The actual is going to be V of 10.1 comma 25.1 minus V of 10 and 25. So this is going to be the delta V, the actual. I'm going to pause and type that in. Okay, so I left the pi in just so we could compare these. So I get 20.150 actually pi. So there we go. That's going to be our actual. So pretty close. Good estimate. Okay, let's go on to the next page. All right, here what we're going to do is take a look at what if we have more variables. It really doesn't change a whole lot. It allows us to do some approximations for more practical things. In this case, for example, we have a situation where we have the dimensions of a rectangular box. So we have the 3 different sides of the box. I'm just going to call this A and B and then C, just to give it something. And so what we're going to do is take a look at the possible error in the volume of the box, given that each could vary up to 0.2 centimeters. So remember, we're not going to look at the plus or minus. We're going to look at the minimum A is 75, the maximum is 75.2, and so on. So our volume now is made up of A, B, and C, and it's of course A times B times C. And we're going to come up with the differential dV by taking the derivative with respect to A multiplied by the differential dA plus the derivative with respect to B times the differential dB plus the derivative with respect to C times the differential dC. And those are all the elements we're searching for here. Okay, so the derivative with respect to A is of course BC, derivative with respect to B is AC, and the derivative with respect to C is simply just AB. And then what we're going to do is set up our formula. So let's go ahead and write down dV, which is going to be BC times dA plus, let's see, AC times dB plus AB times DC. So lots of different pieces there. Let's go ahead and plug in all of our values. So we have B and C. So B is 60 and C is 40. dA is 0.2. And actually, maybe instead of having so many decimal and multiplications, we'll just do that. A is 75 times C is 40, and that one varies by 0.2. And then 75 is A times 60 is B, and that one varies by 0.2. Okay, I think I have all the elements. I'm just double checking here. Okay, so when we start to calculate this, this is a little bit more difficult to do in our head. So for example, we want to look at 60 times 40, and actually maybe what I would do is do 40 times 0.2, for example, which is 8. That's a little easier, I think, and then times 60 would be 480. So that'd be our first one. We have a similar thing for the second one. So 40 times 0.2 is 8 times 75. That one's a little bit harder. Let's see, that's going to be 40, 56. That's going to be 600. And then for our last one, we have 60 times 0.2, which is going to be 12 times 75. Let's see, well, 75 times 6 is 450, and then we multiply by 2, so we have 900 there. Okay, so then we're just going to add up all of those parts, and that will be, let's see, that's going to be 1980. Okay, so that's going to be our differential. That's our approximate. Okay, just to compare, let's do the actual. So the actual delta V is going to be V of 75.2, 60.2, 40.2 minus V of 75, 60, and 40. So I will go ahead and put that into my calculator. Okay, so what I get is 1987.008. So a little bit further off there, but still a pretty reasonable estimate. That's the actual. Okay, so that's going to be your differentials. All right, that is it for this video. I'll do one more really fast video on the parametric surfaces, and we'll be done with this section. Thank you.